Recording in progress.
Okay, great. I think it's a good time to start. So hello, everyone. Welcome back to the first session in the afternoon for today. I'm Raymond Hu from the University of California, Santa Barbara. I will be chairing the first session in the afternoon today. So our first speaker is Lisa from the University of Bath, and she'll be talking about anisotropic diffusion equations for label propagation. So I saw already Lisa in the room. So now the stage is yours, Lisa. Welcome.
Thank you very much for the introduction, and thanks to the organizers for giving me the opportunity to present here. Yeah, as the title suggests, I'm going to talk about anisotropic diffusion equations, which we use for label propagation, and more specifically, kind of the idea is that we look at models arising for collective behavior in nature. So examples of those types of models can be used for looking at very large numbers of animals which are interacting with each other in some way, like very large numbers of ants or schools of fish or swarms of birds or bacteria are all examples of kind of animals which form some kind of collective behavior, or more specifically, we're interested in understanding the interactions between these very large numbers of animals. But the idea of my talk is that, in fact, we cannot only look at very large numbers of animals interacting with each other, but also use this as a motivation to study label propagation, where in the end, if we have very large numbers of data points which are related to each other in a certain way, the hope is that we can use similar models to this to kind of describe label propagation as well. And so basically the idea is that while in biology we often have very large numbers of interacting particles where the interactions are generally over shorter distances, and we usually have rather complex patterns as the result of stationary patterns which occur, that we can use similar ideas which arise in those biological models also for label propagation. So the main idea is that we kind of consider now some is this better now? No, I think there's still this doubling noise. So basically, what we are looking at is that we want to understand collective dynamics, and for this we are kind of studying semi-supervised learning. So the idea is, instead of kind of looking at n animals, we are going to look at n data points, and some of them are already labeled previously, and now we want to understand how label propagation works using those biological models. So more precisely, we assume that we have n plus m data points, and we already know in advance that those data points are somehow related to each other. So more specifically, the idea is that we can introduce some kind of similarity measure between each pair of data points. So let's say we have some data point xi and some data point xj. Then we can introduce a similarity measure wij to describe how those two data points are related to each other. And this allows us to construct a graph based on this underlying similarity measure. So just as an example, if we had a very large data sets of handwritten numbers between 0 and 9, then kind of in order to come up with some kind of similarity measure, what would be kind of obvious is that if we have similar numbers, like for instance, all those zeros are more or less similar to each other, or kind of equal numbers in general are similar to each other, then whereas kind of other numbers like 0 and 7, for instance, are not so closely related to each other. And this allows us to kind of write down a graph structure as what is kind of shown here on the right-hand side. So basically the idea is all those ones here at the bottom are quite closely related to each other, whereas kind of at some point, some of those ones already look quite similar to the number 7. And then all those 7s more or less look similar to each other, but then some of those 7s already look quite similar to the number 4. And kind of so on. This kind of allows us to come up with a graph structure based on the similarity on how close the different data points are to each other. And now, once we have kind of constructed this underlying graph, the question is, how can we partition the graph using inspirations from those biological models? And very crucial tools for studying underlying graph structures are the so-called graph Laplacian, which is kind of written over here in its discrete form. But since we are kind of generally interested in very large numbers, what is often of interest as well is to study the associated continuum limit. And then one can write down the associated generalized continuum Laplacian, which in this precise form depends on several parameters. But for the specific choice of p equal to 1, q equal to 2, and r equal to 0, in fact, one can show that this discrete Laplacian has the continuum limit as given over here. And there's actually already a lot of analysis available on the eigenvalues and eigenfunctions of these continuum Laplacians, which have turned out to be very useful for clustering. But in fact, we won't focus so much on eigenfunctions in this talk, because in fact, if you are interested in unsupervised learning, then the basic idea is that you want to understand the core structure of some underlying set of nodes. And in order to do this, spectral clustering is very useful, where basically the idea is that you determine the first k eigenvectors of the graph Laplacian, whereas what we're mainly interested in this talk is supervised learning, where we assume that we have a certain number k of labels given, and we assume that m labeled points are given, which we kind of denote by xn plus 1 to xn plus m. And now we want to find labels of all the unlabeled points x1 to xn, where generally speaking, we assume that m is much smaller than n. So we have only a really small number of labels given, and now we want to infer how the labels would look like for all the remaining points. And in the literature for this, it has been suggested that you should look at minimizers of some functional consisting of one term containing the graph Laplacian, as well as one fidelity term depending on the given labels L. So just as an example for the fidelity term, here the idea is that we have some kind of given labels, let's say just for looking at something easier, we have some labels -1 and 1, and we know that there's some kind of subset V1 prime of nodes which are all labeled -1, and we have another set of nodes V2 prime of nodes which are all labeled 1. And now, as a fidelity term, we look at the functional given here at the bottom. So we compare the distance of all ui's in that set V1 prime to the given labels, and similarly for V2 prime as well. So once we have kind of looked at the general setting, one important result which is already available in the literature is in terms of gamma convergence on fixed general graphs. So here the idea is that if we have a functional of this form, where kind of the first term already looks very similar to what we have discussed before, whereas the second term is some scaled double bell potential W. So a double potential is a function with values at 1 and -1, for instance, so that basically this function is 0 at those points, and otherwise, especially outside this given interval of -1, 1, the function value is extremely large, so that basically there's some kind of cutoff involved in here, so that if you want to minimize a functional like this, all the labels will be constrained between -1 and 1. And kind of given this functional with this coefficient 1/epsilon, one can show rigorously that as epsilon goes to 0, the limit is given by the functional given over here. So basically, this means that all the labels will be -1 or 1. Then kind of this first term is satisfied, whereas otherwise the function will just blow up. And in fact, a result like this, which was proved by Van Gennep and Bertozzi already a few years ago, is an analogy to the gamma convergence of the Ginzburg-Landau functional. Now bringing things together, kind of, one might not only look at those first two terms, which we've already discussed before, but one might also add a fidelity term. And then one ends up at a gradient flow structure associated with the Allen-Kahn equation with a fidelity term, which is kind of the equation which is given down here. And again, one can both develop computational methods for minimizing this Ginzburg-Landau functional, or alternatively, people have already developed graph-based MBO schemes for solving the limit as epsilon goes to 0 numerically. Now you might wonder, how might all of this, what I've kind of described so far, might be related to those biological models. And so here kind of the idea is that now we are considering n data points where m of those points are already correctly labeled, and we assume that we have a very small number of labels. And we want to understand how information propagation works of those correctly labeled points. And instead of kind of looking at those very large particles which usually kind of move around a certain domain, we now want to introduce a characteristic function which kind of is associated with each agent I. And this characteristic function should kind of mimic which label is the most realistic one of a specific point. We also introduce an interaction radius epsilon and an influence function wij, which can be regarded as some weights depending on a certain position xi, xj, and the interaction radius epsilon, with the idea that if two points are not really related to each other, then the associated weight should be rather small. And the interaction radius epsilon, which is also in there as a dependency, kind of can be more or less regarded as some kind of cutoff. So if, again, if points are very far away, then they don't really influence each other. And then we can kind of look at interacting particle models, which are motivated by this equation over here. So UI is our characteristic function for each agent, where we kind of look at the change of this label UI over time, which depends on the labels of neighboring nodes, or nodes for which those Wij's are rather large, because otherwise the terms are not really considered in this very large sum. And in fact, these types of models are already very well known and have a lot of similarity to Cocker-Smell models or Krause's opinion formation model. So basically what we are going to do now is to kind of look at this very large number of points x1 to xn plus 1 on some kind of bounded domain, where we assume that we have a given number of labels L1 to Lk, where the number of labels is generally rather small. And then we also assume that we have some kind of labeled sets of points already given, which are associated with each label. So for label Lj, we assume that the associated subset of points with this label is given by Vj prime, which are all kind of subsets of V. And just for consistency reasons, we also assume that one point cannot be in several of those sets. So this means that the intersection of Vi prime and Vj prime has to be empty. In addition, we assume that we have some kind of connected weighted graph G given, which consists of the nodes V. So those are just the points x1 to xn plus m, some edges E, and the associated weights based on kind of this graph structure which we looked at earlier. Then we kind of write down the mathematical model as given over here. So this is basically also what has been done in those biological applications, where we consider du I dt equal to gamma times the sum over all possible interactions which can take place. And motivated by the literature on clustering, it's very desirable to have some kind of cutoff. So this motivates to add this additional term depending on the double well potential W, which basically restricts those values UI to be between -1 and 1 if we consider a double well potential of the above form, where the values are at 1 and -1. And then as last thing in terms of the mathematical analysis, which is often very helpful, is that we do an appropriate scaling. So if we kind of consider the sum over m plus m entries, then it's desirable to scale this sum by m plus m. Having kind of this functional as a starting point with the boundary conditions kind of given by ui equal to -1 on this set y1 prime and ui equal to 1 on this set v2 prime. If you only consider two possible label classes for now, then another condition we need to kind of think about are the initial label distributions. And here, if you kind of want to consider a rather unbiased approach, the idea would be that all the nodes which are already labeled would be in those sets v1 prime and v2 prime, whereas whenever you don't really know anything about a point, then you might just consider homogeneous initial data. So you might consider ui of 0 being equal to 0. Then kind of giving this entire system where kind of ui for I equal to n plus 1 to m plus m is kind of already given through these boundary conditions. The question is, if we kind of solve this above ODE system, how we can see what happens in the long term. And for this, one can either look at the energy functional as given on the bottom over here, but as you can kind of see, it's already quite complicated, or one can consider the associated limit as n goes to infinity and epsilon goes to 0. And we have kind of derived the limit both formally and rigorously based on both the energy formulation and the ODE system. And what is very important for looking at the associated limits is to come up with an appropriate distribution rho of the density of the data points. Then we introduce the associated empirical measure, and we also considered an interpolation of this function u, because initially it was only kind of known on those specific data points, whereas now in the limit we would require a formulation on the entire domain, and this requires some kind of interpolation on those points where there's no data point. And of course, we also need to scale everything accordingly, depending on how epsilon shrinks. This type of procedure can be extended to more general cases. So right now I'm mainly restricted myself to 2 labels, but similarly, you could also consider multiple labels. And in terms of initial and boundary layers, you could also extend it in the sense that depending on how the initial conditions are chosen, we actually see a different behavior. But basically, based on kind of those arguments, one can come up with a limit in energy functional and L2 gradient flow. And in fact, it turns out that the first term of this L2 gradient flow is related to an anisotropic diffusion operator as given over here. One can also do some numerical simulations, but before that, I'd like to kind of shortly outline some of the theoretical results we obtained of the system. So first of all, one can show existence and uniqueness of solutions. One can also show consistency of labeling. So what I mean by this is that if you look at the stationary solutions, then we observe a very similar structure between the stationary solution U and the given density rho. So basically, if there are no particles, so if the density rho is 0 in a certain subset of the domain, then also the label function U is equal to 0. And this also holds the other way around. So if the density in a certain subdomain of the domain is positive, then the label function U in this case is also non-zero, which is consistent with the fact that our labels were 1 and -1. So in fact, it will always be closer to one of those given labels. We also investigated a maximum principle and proved that solutions can attain their maximum and minimum on the parabolic boundary only. And last but not least, we also looked at the dependence on the different parameters in the model, and we found out that the edge weight Wij and the parameter gamma actually can be regarded as a scaling in time, whereas the coefficient of the double well potential is more or less a regularization parameter. So basically here the idea is as this regularization parameter goes to infinity, we will basically have step functions as our stationary solutions. To kind of see a bit better of what's going on, here are some numerical results. So first of all, kind of if you assume that we have no initial bias, we only have kind of 2 points which are initially labeled. It's a bit small in here, but for instance, if on the very right left, we have a point which is marked in blue, and on the very right, we have a point marked in orange, and all the other points which are in green are 0 initially, then one can kind of see very nicely that there are kind of 2 clusters which form, one blue one and one orange one, which kind of can be regarded as the unbiased case. So if you don't know anything about which cluster the points might belong to, this procedure seems to be very well. Whereas if you kind of start with normally distributed initial data, then this initial data is absolutely not what the resulting clustering should look like in the end, because as you can see, there's a lot of orange, and then in the end, the stationary solution is also mainly orange, and those 2 different clusters haven't really been detected at all, which can be attributed to the fact that the bias was just too strong in these examples. And in those 2 examples at the bottom, we basically have the same behavior. If we have too much bias going on, then the correct labeling might be found as kind of here on the right-hand side, but not necessarily as kind of this example on the left-hand side shows, that we basically have too many clusters. On the right-hand side, we have a tiny cluster, and on the left-hand side, we have a tiny cluster, and then the 2 big clusters in the middle. So this basically shows that the choice of initial data really influences how the patterns will look over time. And this also motivated to consider 0 initial data for most of the following numerical experiments. So basically, whenever you don't know anything about what's happening, you just put homogeneous initial data. And in this plot, we investigated the dependence on the label location. So basically, this example here on the left-hand side was more like a test case of what would actually happen if both labels are in the same cluster. And then again, the 2 clusters weren't really found. Whereas even if the 2 labels are very close to each other, but in distinct clusters, then in fact the associated clusters were detected. Then the question is whether there's a consistency between the microscopic and the macroscopic approach. And indeed, we observe that as kappa becomes larger, we have more like a step function as a solution, which is also corresponding to the analytical results we obtained. And what you can also...
It's 7 o'clock.
That this is very close to the associated macroscopic model.
Lisa, you may have 2 more minutes.
Okay, yeah, that's fine. And what we also did was studying the associated stationary solutions of the macroscopic model. And here you can see, again, what we kind of also observed in the analysis. If you kind of have 2 clusters, so in green you can see row now. So for instance, we have a cluster on the left and a cluster on the right. Then depending on how you choose this kappa, you either get kind of a step function or something significantly smoother than that. You can also apply this types of model to more complicated underlying distributions. For instance, in the 2-dimensional setting, you might consider the 2 moons data set where a few points are initially labeled. and all the others have kind of homogeneous initial data where you can kind of see those clusters as the stationary solutions, which can both done in the microscopic setting as well as also in the macroscopic setting. And you can also use a very similar approach to study multi-label data sets, like for instance the MNIST data set, which I motivated initially, where you can use a very similar approach using kind of the same model to classify those multiple labels. So just to sum things up, the idea was that motivated by biological models, we looked at label propagation, where we connected collective dynamics on the one hand and graph Laplacians on the other hand. And basically, this methodology kind of combines different well-established areas of mathematics, and using both microscopic as well as continuum models, we could also get some insights into the underlying dynamics using mathematical analysis to characterize the behavior of the solutions of the continuum model. And we also used some numerical simulations which illustrated that in fact there's a correspondence between the microscopic and the macroscopic equation. Thank you very much for your attention.
Great. Now let's see any question from the audience. Thank you for giving this nice talk. Maybe let me ask a quick question. So when you are training your data for the label that you already know, do you assume that the correct labels, or there could be some noise? I believe it.
So far we assumed that we have the correct labels, but as you kind of saw in those numerical experiments, if they were incorrectly labeled, then things might actually go wrong.
I see. Okay. And then what would be the interpretation of your characteristic function, this UI of t, if you are using this to modeling like the flocking behavior of animals, for example? Well, would there be an interpretation?
Well, the interpretation would be more in terms of the positions of the particles.
Okay, I see. I see. Oh, thank you. Other question from the audience? Okay, great. Now, thank you again, Lisa, for giving this nice talk. And then could you please stop sharing?